Now there's another theorem we'd like to look at. That's theorem 4. Now supposing we have a circle like this. Okay. And then we have quadrilateral inside the circle. Well, in circle geometry, we call this a cyclic quadrilateral. So this is A, B, C, D. Now this theorem says that if we have a cyclic quadrilateral, then angles on the opposite side are supplementary or add up to 180 degree. So I'm just labeling them. But just understand that opposite angles like x and y are supplementary, meaning that x plus y is equal to 180 degrees. So we can say that theorem 4 shows that angles in opposite segment are supplementary. Okay. So that is theorem 4. So if we have a question like this, so let's see, the question is something like this. Okay, so it's not drawn to scale. So please note that the lines must actually touch the circumference of the circle. If not, then this theorem or this rule will not work. Okay, so let's assume the lines touch. So if here is 70 degrees, and you asked to find here x, based on the theorem, we know that opposite angles are supplementary, or the opposite angles are sum up to 180. So we have 70 degrees plus x. Let me write this well. 70 degrees plus x is equal to 180. So that means x is equal to 110 degrees. So if you also have a value here, or let's say you have a value here, 30 degrees, then opposite here is 180. The sum of this two will equal to 180. So that here will become 30 degrees plus, let's say this is y, equal to 180, and then you know y is actually 150 degrees. So that is the point of this theorem. But what if you now have a circle like this? Okay, so where you have a slight cyclic quadrilateral, okay, inside the circle, but this time it is extended outside the circle. So the baseline is extended outside the circle. Now this is also another theorem we'll call theorem 5. Okay, so if you have angles here, another angle here, theorem 5 says that the exterior angle of a cyclic quadrilateral, okay, is equal to the interior, opposite angle. Okay, so meaning that this angle here, this is the exterior, is equal to the interior opposite angle. So remember, it must be a cyclic quadrilateral like this first. Then if it has an exterior here, then this exterior angle is equal to the interior opposite angle. Okay, so basically if you have, let's say, a question like this, we're going to be doing a lot of exercises, but let's just look at something quickly. Oops. So if you have a, yeah, okay. So if you have something like this, okay, and then here is 50 degrees, then the exterior angle will also be 50 degrees. So that is the point of this theorem. So we're done with the basic theorems in circuit geometry. But now let's look at the tangent theorems. Now, one of the first tangent theorems we like to consider is something like this. So this theorem says that if you have a tangent, so let me draw. A tangent is actually a line that comes across the base of a circle. So it's a straight line that comes across the base of a circle, or a line that touches the base of the circle as a tangent. Now for this, now if you have a radius from the center, drawn from the center of the circle, meeting the circumference and touching the tangent, let me draw that well, and touching the tangent, well, we say that the tangent is perpendicular to the radius of the point of contact. So that would be, let's call that theorem 6. Meaning that here will be 90 degrees. That's just a point. So theorem 6 says that a tangent is perpendicular to the radius at the point of contact. So you understand that means that here will be 90 degrees. Okay, here also will be 90 degrees. So if the radius comes in contact with the tangent at this point from the straight line here, touching the circumference and the tangents, then you know that they are perpendicular. It is perpendicular to the tangent. Okay, so that is theorem 6. Now there's another tangent theorem I'd like to show you. There are a lot of them, but we're just going to show you a little bit of them. So let's say we have another circle here, and this time we have angles from here to here, and then another angle here. Let me try that well. We have here, we have here, and we have here. Okay, and we also have a tangent here. So let's say we have an angle here, and we also have an angle here. Now this theorem shows very well that the angle between a tangent here to a circle and a chord through the point of contact is also equal to the angle in the alternate segment. Now where is the alternate segment for this angle here? Now this is it here. So meaning that this angle here is equal to this angle here. So if this is A, this will be A. The same thing for this part of this. Since this also forms a chord, so the angle to the tangent and the chord is equal to the alternate segment. So if this is B, this is B. So it's just almost like the one we did with the cyclic quadrilateral. Okay, so the cyclic quadrilateral was the exterior angle of a cyclic quadrilateral is equal to the alternate segment. But for this one, about the same thing, but this one has to do with a tangent. So if you recognize a tangent here, then you see there's an inscribed angle, like a triangle here, and this angle here is given. That means if it has an alternate segment like this, then they are equal. So theorem 7 shows that the angle between a tangent and a chord is equal to the angle in the alternate segment. Okay? So let's see if we can get an example of this. So you have a circle like this. Okay, let me draw this from this point. Okay? And you have, oh, forgot I was still using the circle function. Okay? So you have a segment, it's a tangent here. And then you have angles to this point like this. Okay? So if there's an angle here, 50 degrees, assuming there's an angle 50 degrees, and they ask you to find an angle, maybe here, x. Well, you already know that this angle here, following the theorem, x will be equal to 50 degrees. Following the theorem that the angle from the tangent and the chord is equal to the alternate segment in the circle. So also if here is y and here is 60 degrees, that means y is also 60 degrees following the same theorem. What you need to understand about second theorem is that you should be able to recognize each of these theorems when solving second geometry problems. So basically, in second geometry problems, you'll be given a problem that comprises of so many theorems. So understanding these theorems will help you recognize what you need to do and how to apply them. Okay?